jetzt gut. Dann ist jetzt ein bisschen so, aber so. Okay. Da sage ich nichts. Okay, ich möchte das mal probieren. Okay. Können wir... Okay, warte. Ich kann mich muten, ist das okay? Kann ich mich muten? Okay, ich mute mich und ich kann nicht lauter stellen, aber ich werde lauter sprechen, ich glaube, weil ich möchte nicht, dass es... Oh. Möchtest du Google Meet versuchen? Na pass mal, mach mal schnell. Wir nehmen diesen gleichen Meeting Room. Hallo, die Kamera ist auch viel, viel besser. Ja, ich mag's. Okay, Skype. File edit. Quit, please. Thank you very much. Okay. Ich möchte nur sehr schnell versuchen, mein Screen zu sharen. Kann ich das machen? Your entire screen. Entire screen. Only share screens. Okay. Okay, kannst du alles sehen? Kann ich das irgendwie... Okay, sieht's nicht. Ich muss das lassen, aber es passt dir. Ist das okay? Okay. Hier versuche ich noch sehr schnell. Ich mache das und ich mache das und ja. Okay, ich bin bereit. Ah, was? Oh, du bist sehr leise für mich. Ich mach's lauter, nur eine Sekunde. Output. Oh, Output ist so schon laut. Ich weiß nicht, warum ich dich nicht so gut hören kann. Ich mache Fullscreen, nur eine Sekunde. Okay, da ist es. Aber du bist sehr leise für mich, nur dass du weißt. Ja. Ich weiß nicht, aber nichts. Du bist leise. Deep Learning Parts. ich möchte Twitch sehen. Ah, ich kann dich verstehen, aber bitte nur, wenn du mir etwas sagst, ein bisschen lauter sein. Okay. Ich weiß nicht. Kannst du mir bitte den Twitch-Stream schicken? Hier in diesen Chat. Ich möchte sehen, ob ich ohne Video die Twitch-Messages sehen kann. Okay, es ist fast 6 Uhr. Twitch TV. Ah, bitte schick es mir. Ich möchte es noch versuchen. Okay, ich finde es. Ich glaube, ich kann es alleine finden. Twitch. Kannst du mir jetzt nur... Okay, here it is. Nice. Learning Cards. Was kann ich machen? Kann ich das? Okay. Okay, warten wir noch für Leute, weil wir haben noch nur 2 Leute da. Ja, ich glaube, es ist okay, wir warten 10 Minuten.
Okay. Hi and welcome to the Autoencoder Magic meetup today, where Halil Beglerovic will guide you through all the different tips and tricks he has with autoencoders, how you can employ autoencoders on your own. You can ask questions in the Q&A. There's a Discord link. You just click on it and then you can ask your questions. So we're trying a new setup. So if you don't see all of the screen, please give us some information. Type something in the chat. And now I hand over to Halil, who is going to lead you through this presentation. Bye.
Okay, thank you very much. Please just confirm that everybody can hear me. So I will wait for a second. No feedback. Hi, can you hear me? Yeah, thank you very much. So I will be following the chat on Twitch, and I will also ask some questions. So it will be cool if you reply, because I'm going to check the replies. Okay, so my name is Halil Beglerovic. Thank you very much for coming this evening. I'm going to talk about autoencoders and Habit and his colleague. They made this cool title called Autoencoder Magic and this cool background image. I liked it a lot. So I have taken this theme about magic, so I put also some magic in some slides. So I just added like this small part here because the image they show is a perfect autoencoder, which never happens. Of course, usually you put in something like this and then you get out a firework, something completely different. But in the end, if you train a lot, hopefully you get the image that they put on the meetup where everything is perfectly like the same. Everything you put in, you get at the output. Okay, so without further ado, I have this short slide about me so that you know who is talking to you. So I'm a research engineer and a Marie Curie alumni. So basically, the difference in this slide from the last time is that I finished my PhD, thank God. So my PhD was on methodologies for testing and validation of automated driving functions, and I used a lot of deep learning in my thesis. So some of that I'm also going to show today. So my interests are deep learning, computer vision, programming, open source software, and so on. So you can find, of course, this presentation is going to be online, available for everybody. So you can then check me out on GitHub, ResearchGate, or LinkedIn if you want. Okay, so what is the agenda for tonight's talk? I wanted to give some kind of introduction to autoencoders and different flavors of autoencoders, and I wanted to maybe show it in a way that you can maybe find a use case where you can use it and then later easily apply it. Also, my talk is really high level. I did not try to go too deep into the mathematics, the formulas, and so on. I really want people to get the intuition behind these approaches, and then later we have a discussion. We can talk there a little bit more, or if we see that people are interested, we can also then make schedule a new presentation where we go really deep in how to derive stuff and so on. So I will start with autoencoders. Then I'm going to talk a little bit about the latent space and what they do, and also show some latent space magic. Then I'm going to talk about sampling for this latent space in the autoencoder. Basically, I'm going to, like, every topic brings up the next topic. So you will see when we try to do sampling from the autoencoder, it's not going to work. Then I'm going to talk about the reparameterization trick, KL divergence, and then variational autoencoders, which are better for sampling. Then I'm going to add categorical, basically we're going to add additional information to the variational autoencoder to sample from different categories. And then I'm going to talk a little bit about unsupervised categorical variational autoencoder. But before that, I have to introduce this Gumbel softmax. Maybe this is going to be the most, let's say, interesting part for some. And also then I'm going to talk about semi-supervised, because we will see that an unsupervised categorical variational autoencoder has some limitations. So let me slowly start then with the autoencoder. So I suppose also a lot of you have seen this. So this is an autoencoder architecture. Basically, you have an encoder and a decoder. Usually what you do is like you have a higher dimensional input, and then through layers you reduce this to some, let's say, smaller size. So let's say if here in the input is 5, we reduce it to 2. And then we go from 2 to 5 again. So basically we want to reconstruct the input. And this is where this encoder part comes in, autoencoder, because basically we are encoding this information. So we're basically compressing information. We take something which is high dimensional and compress it to something which is low dimensional. And we will see why this is actually a good idea. And yeah, what the latent space later can, for what can it be used for? Okay, so basically, the encoder, in order to compress this data, he needs to learn about the data and learn specific characteristics about the data so that he can compress it, basically. So let's say I will later work with images, basically the MNIST data set, and you will see that the encoder actually has to learn like some characteristics for the number, say 1 or number 0. And then based on these characteristics, he's going to put them in separate, let's say, places in the latent space. And then this information is going to be used by the decoder. Basically, the decoder then has to take this low dimension information and return the whole output. By doing this, like compression and decompression, the network has to learn a really good latent space, because if the latent space is not good, the decoder will not be able to recreate the input. So this is like, let's say, fully connected autoencoder, but today we are going to, or tonight we are going to work with convolutional autoencoders. It's the same thing. The only difference is that we are using convolutions rather than fully connected layers. Everything is the same. Now we have a 2D input. Basically, in our case, for the MNIST, it's going to be 28 by 28. With convolution, well, convolutional layers, we convert it to a lower dimension. Again, this is the latent space, and then the decoder uses this information to reconstruct the input. Basically, the loss is then comparing the input to the output. They have to match. Okay, so here I have like a small sketch to talk a little bit about how this actually works. So let's say we created the architecture, like the convolutional autoencoder, and now we feed in some images. And of course, at the beginning, we have some random initialization. So what is actually happening inside? So we pass in a number, let's say 7, and okay, let's say 7 and 1, doesn't matter, like 7 or 1. What happens is that, of course, it goes through the layers, and then at the end we have a 2D, let's say, latent space. Of course, this you can define. I use 2D because it's going to be easy to visualize. Normally, you use a much higher dimensional latent space because it's going to be easier for the encoder to encode and the decoder to decode the information. Basically, with this, you're really limiting, let's say, the encoder and decoder. We're really pushing them hard because we're giving them only 2 dimensions. So what's going to happen is that we pass 7 and 1, and they end up somewhere in this latent space. Of course, because it's random, it can be anywhere in the latent space, but here I'll just put them here in this part. And we say, like, these 2 numbers, they represent, let's say, this 7. What happens then is that the decoder gets these 2 numbers, and at the beginning, he's really bad at reconstructing these numbers. But during training, of course, with backpropagation, the decoder gets better at reconstructing the number. And also what happens, because 7 and 1 are somehow similar, the only thing here is like this line here, which can also be really small. This information gets propagated back to the encoder, and he is going to try to separate these as much as he can, because he's going to make the life of the decoder easier. So because if these guys get pushed away, then the decoder will know, okay, if I get something from this part of the latent space, it's a 7. If I get something from this part of the latent space, it's going to be a 1. So we can immediately see that this is really nice for clustering, because later it's going to be much easier to cluster these numbers. So we go for a really high dimensional space, 28 by 28, to a really low dimensional space, and then we can see that we will see later, that we get separate clusters for each numbers. And I mean, this has to happen because there is no other way that the decoder can recreate the input if these guys are not separated enough that he knows, okay, if I'm in this part, I will get a 4, and if I'm in this part, I will get a 9. Okay, maybe it's not so intuitive now, but I'm also going to show it in code, so I think it's going to be much easier to understand. So yeah, this is what I said. So one application of autoencoders is basically clustering. So you have some kind of input, and then he separates them in cluster based on similarities in the, let's say, the input space. Okay, so now I'm going to jump into the code. Okay, so I this was a mistake. So I went all the way. Can I go to the beginning? Okay, I went all the way to the back. So let me go back here. Okay, and now I jump to the code. Okay, so I prepared these Jupyter notebooks. They should be really straightforward to use. So for each type of autoencoder, I made one notebook, and yeah, basically by running the whole notebook, you can recreate all of the results I made. So let's see if this will. Maybe I just restart it quickly. Okay, so restart it. Let's run it. Okay, it's running. So I want also to. Yeah. Yes, I can. Okay.
So it looks like we've lost connection to Halil. Just give us a second. I'll bring him back in. So what was the last thing you saw? It has to be, I think it was about that you were explaining the latent space and you were trying to push apart the 7 and the 1.
Oh my God, okay. So that was a long time ago. I didn't even know. Yeah, I didn't know that I disconnected. But okay, so let's go. So I want to push part 7 and 1. So what is happening is that after the random initialization, we would get a jumbled mess around here. So all the numbers.
Share the screen. The screen.
Okay, so screen. Okay. Entire screen. Okay, just let me know when you can see it. I will monitor this guy now just to know if anything happens. Okay, no problem. Okay, just a second. I'm going to have that also open. Okay, perfect. Okay, so after random initialization, these numbers are going to be everywhere in the latent space because there is no rule where they should go. And the decoder will have a really hard time basically recreating this input. So let's say if you get a 7, he's going to be here. If you get a 1, he's going to be here. And the decoder will slowly learn how to reconstruct the input. But also the encoder will learn how to put these guys in a neat location so that it's easier for the decoder. So he will maybe put all the 7s here, all the 1s here, and so on, so that the decoder, when he sees, okay, it's coming from this part of the latent space, I know this has to be a 7, and so on. So basically, the encoder and decoder are playing together in such a way to create a latent space where it is easy to decode the input. So encoder gets, let's say, an 8. He puts it somewhere here. The decoder knows, okay, if I see something here, it's an 8, and so on. Okay, so you immediately notice one thing. So the autoencoders are really useful for clustering because you take something which is high dimensional and can convert to something which is low dimensional, and the autoencoder learns also features which are important for, let's say, to put it in a certain location. Okay, now I show you the code. Basically, I have for each type of the autoencoder, I created a Jupyter notebook, and yeah, if you want to recreate all the results I made, you can just run this one notebook, or for each of them, the notebook. I'm of course not going to retrain because I already did it, and I also in this 8 minutes I went through this, so I'm just going to. Okay, actually I have to explain it. So this is just importing libraries. This is just downloading the data, basically the MNIST dataset. Here is where I create the autoencoder. Basically, it's just several convolutional layers followed with a linear layer. It's the same, so the encoder and decoder are basically the same, except that I had to add output padding so that I make the dimensions the same. So basically encode, decode, the forward run basically this, take the input, encode it, and then decode it. The latent space for all networks is fixed to 2. So we always have a, let's say, latent space that we can visually inspect. Here I load, yeah, this is, here I loaded the model, but so I created the model, but didn't load my weights, so the train weights, because I wanted to show you how does it look like if you just run it when it's randomly initialized. So you can see that the numbers basically are all over the latent space. Here are the colors represent the numbers. So what the encoder and decoder have to do is they need to put this in some kind of order so that they know how to reconstruct the data. So here then I loaded the weights for the model, which I trained previously. And here is how the latent space looks now. So one thing that which you can immediately notice is that first, the sizes here are really big. I suppose these are outliers. I didn't check them, but I suppose they are outliers, and that's why they got pushed really, really far away. But what is interesting for us is if we zoom in a little bit, so I'll zoom in a little bit more. Okay, so here what we notice is there is some kind of order now in the latent space. So let's say for this number 0, it seems like we have 2 clusters. One is on the right side, one is on the left side. And yeah, there are somewhere around +4 on the y-axis. So the encoder, when he sees a 0, he puts it somewhere in here. And the decoder, when he sees 2 numbers coming from either here or here, he knows it's, let's say, a 0 and how to reconstruct it. And all of these, let's say, movement in the latent space, they represent some kind of change of shape or change of features of a 0. So a 0 from here could be, I don't know, small and thin, and a 0 here could be big and let's say, thick. So this is how it was encoded basically. And we can see here that we also have some nice clusters which can be easily, let's say, separated when we compare it to here. So this cannot be separated. This can be easily separated with some kind of clustering algorithm. So basically here I just show what the latent space looks like. It's just basically two numbers. So for each image, you will get two numbers, putting it somewhere here in the latent space. So let me run this again. Yeah, it's the same. So what I want to show you now is I have taken from the test set 10 unique numbers. And I want to see, like, these are the original numbers. I want to run them through the network and see what is the output. So how good is the reconstruction of the output? So I will run it again. Yeah. So we can see that for some numbers we get good results. For some numbers it is a 3, but it's a little bit changed. So it's not the perfect fit. For some numbers we will see we have an error. So basically somehow the encoder confused, or the decoder is confused, and for a 5 he creates a 6 and so on. And the same happens for the 8. So I use this example just to show you that it's not going to be perfect. And usually what you want to do is you want to train a lot, because the model basically cannot overfit here. You want it to overfit. You want the input to match the output as best as you can. Okay, so we can see that, again, we get decent reconstruction, so we can go now further. What I wanted to show here is that we can do some nice interpolation inside the latent space. So we can somehow smoothly go from a number 7 to a number 1. So this would represent, let's say, where is 7? 7 is this, and 1 is red. This is 7. Yeah, I don't know where 1 is, maybe below. So you somehow move through this latent space, and for each movement you recreate the image. So we get something which is, let's say, between a 9 and a 7. So here we had the 7 like this, and then this upper part gets shorter, shorter, shorter until it turns into a 1. Another example, if we have a 0 and we want to turn to a 6, you see that he starts by opening this part and then making slowly a 6, and then curling it up a little bit until we get to the 6 we want. So basically this is this 6 here. So it goes from 0 to 6. So this kind of interpolation is not possible in the, let's say, the image space, because you will not get this morphing. Basically you would get an overlay of a 6 and a 0. But if you do it in the latent space and for each step reconstruct the, let's say, the output, you get these kind of nice transitions. So this is a way also you can create new data. Maybe this 6 does not exist in the data set, but you can also get it by moving through the latent space, let's say. Here's another example going from a 4 to a 9. Basically he just closes this loop here. Closes this here, and then shifts this, or tilts this a little bit to the, let's say, I don't know, counterclockwise. So what I wanted to show here is that we can also do some latent space arithmetics. So here is the 1, which we have originally from, let's say, our unique numbers. So this is this one. But can we augment this one in a way that we want? So I have here an example. You see this 9 here and this 9 here. It is rotated a little bit counterclockwise. So what would happen if I take this 9, subtract it from this 9, and then add it to this 1? So we have a 9, we have a tilted 9. When we subtract these two, we get the output is tilted in quotes. So basically the output is tilted. And if we add this to our 1, we get something interesting. So basically we take our 1 9, another 9, subtract it. I also multiplied a little bit to make the effect a little bit larger, and then give this unique 1. And what I get as an output is, it's not only tilted, but it is also a little bit thicker. The thickness is not something what I wanted, but at least the tilt is here. And I will show you, hopefully, if it works. I think it should. Yeah, so I will show you a 6, and let's try to tilt this 6 also. So here we take now the 6 instead of the 1. So what did I forget? Okay, I didn't run this, so let me just run these cells really quickly. Okay, run. Okay, let's try. Okay, the 6 is okay, and let's run this. You see that this 6 really gets, let's say, rotated counterclockwise. Yes. I'm not seeing it actually being done. Yes, but Okay, please. I can hear you. I can hear you, and I also see the question now. I think it can be, it is applicable, but basically, what I saw is that you use LSTMs. So basically, you would use an LSTM to encode the time series data. Basically, sentences are not time series, but they are basically something which goes through time or which has some kind of order. So you would use, let's say, LSTM or some other, let's say, recurrent network, and then you would encode that, and then you would, from this encoding, you would use this as your latent space and decode it. I've used it also, but the problem with LSTMs is that they have, like, if you have a really long sequence, they tend to forget. So this was the main issue I had. But basically, they can, and they can also do this kind of arithmetics, and they do it, yeah, quite nice. Also, the problem only with LSTMs and why we have now transformers is because they forget, and also the, let's say, the how do you call it, the attention and so on. But basically, yes, it can be applied, and I also used it, and I also have some time series. I've done it previously with some time series where you encode it and decode it, and then you do some time series interpolation and so on. Okay, can you please repeat the question before you answer? Have you tried to run on vision tests? Okay, so this maybe I will answer in the discussion we have later, because I have to go forward. We have many more stuff to go through. Okay, so this is really important. So let's say, what happens if you want to sample from this latent space? Of course, we can sample from this latent space. So if you take a number from here, we will get a nice number out. But the problem is we need to know where these guys are. Basically, we would have to consider, like, we can look at this as a distribution. We could model this distribution and then sample from this distribution, but you will see that it's really hard to do. Like, sample from this, creating this distribution is really hard. Maybe we would have to use a Gaussian mixture model or something. What would be nicer is if we could shape this latent space in a way that it could be useful for sampling, let's say. And this is what I'm going to talk about in the variational autoencoder. I just wanted to show you what it looks like when you sample from a space, from a point in the latent space where the network did not, which the network did not use before. So we get some kind of garbage out. So this would, like, I sampled here from a normal distribution, and you already saw that around 0, we have a really bad, we have no points there. So because we are sampling in this, let's say, space where the network which the network did not use, we get this kind of garbage out. So now the question is, can we basically use, can we force the latent space to have some kind of shape where we can easily sample from? And this is basically what I'm going to talk about next. So can we change the distribution of the latent space to make it easier to sample? So this is the question. And the answer is yes, we need to sample the latent space. So basically, while we are training, we need to sample the latent space and force it to take some distribution, let's say a normal distribution. And also we can enforce this by using the Kullback-Leibler divergence in the loss function. So basically we force it with the KL divergence, we force a normal distribution. So here I put this in red because this sample is really important. Normally you cannot sample inside a neural network, so how do you do that? And also the KL divergence, I will not go into code or also into the equation. So basically what this gives you is a difference between two distributions. So you can compare two distributions. You can compare, let's say, a distribution A with distribution B, and then you will get some kind of output out. And the lower this output, the better. So basically, I will use this as plug and play. Maybe later in discussion, we could go deeper into this, or if you need another presentation, then we can also talk about this. But basically, just remember this KL divergence it gives us the difference between two distributions, and we can force two distributions to be the same if you use this in the loss. Okay, so sampling from inside a neural network. So I took this image from this paper called Categorical Reparameterization with Gumbel Softmax, because I'm going to use this later again. So here we have one is a normal neural network. You go from top to bottom, and it's differentiable. So you have here these deterministic differentiable nodes. I will skip this for now. Actually, yeah. So here, this one is important. So what if we have, let's say, some layers, and let's say we create some mu and sigma, and we want to sample. We can do it of course, in the forward pass, but in the backward pass, we cannot pass gradients through a stochastic node. So basically, it's not possible because the gradient is undefined. But basically, what you can do is you can do this reparameterization trick, where you create, let's say, the mu and the variance, and then you sample from a normal distribution and add this. And so you add the, let's say, the mean and multiply the variance. So basically you get a sample, which seems like it has been sampled from your normal distribution, but basically it's just a combination with the, let's say, normal distribution and your output. So basically this is called the reparameterization trick. So now the gradients can flow through this network, and we have our stochastic node here isolated. So basically no gradients need to flow anywhere behind it. So the only thing which we are optimizing for is then this mu and the variance. Okay, so let's go further. So this is how it basically looks like. So this is the variational autoencoder. So instead of now having one, let's say, having only two numbers as an input, like the latent space, basically we create two numbers, like a mean and variance, 2 times 2 actually, the mean and variance. And what we do is we sample from a normal distribution, add the mean, multiply the variance, and then sample from this distribution, and then try to reconstruct the output. So what happens, like a 1 comes in, we have a mean and variance for this one. We sample from the normal distribution, and then, like I will say, we sample from this distribution, and then this gets passed to the decoder, and the decoder has to then reconstruct the input. So what happens now is that we force the network, or basically we force the autoencoder to have a latent space with which is normally distributed. And you will see later how this looks like, and then that we can really nicely sample from this distribution, and we will have no, let's say, no garbage outputs. So let me go to the code again. So this is now the variation autoencoder. I'm going to quickly go, sorry, I will show you how the network looks like now. What are the differences? This is exactly the same. No, here, this part is exactly the same, no difference. Here now we have now two additional, let's say, not layers, but branches. So one is for the mu and one is for the variance. So basically for the mean and variance. And the decoder is basically the same. So the decoder gets two numbers and he tries to recreate the output. And how does it look like now when we run the encoder? Basically, we get a mean and variance. And what we do here is, this is the, yeah. So here is the place where we basically sample, and there is nothing, like it doesn't, no gradients have to flow behind this. What is important here is that we multiply this, let's say, random, this normal distribution, we multiply with the standard deviation, and then we add the mu. Yeah, basically this is why I make a mistake before. It's not the variance, it's the standard deviation. So basically multiply this by the standard deviation and add the mean. Okay, I actually want to, okay, there is nothing to run. So I'm just going to show the output from here. So this is how our new latent space looks like now. So if you remember here in the autoencoder part, this is how our distribution looked like after training. And here is our distribution after training with a variation autoencoder. So you can see that all of the numbers are put in a nice location inside this, let's say, normal distribution. So if we sample from here somewhere, we will get one number. If we sample from here, we will get another number, and so on. And here I'll show how sampling actually looks like. And maybe I will run it quick. I will run it quickly so that we can create some random samples. Let me check if this is, I'll just shut this one down so it doesn't interfere. Okay, so let's run this one. Okay, it's running. So load the data, create the model, load the model. Now we create the model and also load the weights immediately. So that you have already seen how the latent space looks like. And here we can create some random samples. Of course, it's not going to be perfect. There are going to be spaces where we do not get any kind of meaningful number out, but usually the samples are really good. So let's see here. And also what you can see that the variation autoencoder is makes this a little bit fuzzy numbers, let's say. So this is something, a difference with the GAN, because GAN is known to make really sharp lines. So this is, let's say, a drawback of the variation autoencoder, that the lines are, let's say, a little bit fuzzy. But as we can see, we can generate numbers from out of here. Yes. Yes. Ah, okay. Okay, so Herbert was talking with me and he gave me some inputs on how to present this better. Okay, So basically we are creating here random samples. Usually, as I said, samples are okay. Sometimes we get a part of the, let's say, the latent space where the reconstruction is not good. And here I have a nice visualization of the latent space. So basically what we do is we create a grid and go through all of the points, and we can then nicely visualize how the whole, let's say, reconstruction of the latent space looks like. So we can see here how it goes from a number 8 to a 1, and then from a 1 to, I don't know, maybe a 2 or something, and then a 4 and so on. And also what we can notice is that, let's say for this column here, it goes from a 7 to a 9, and then it also goes from a 9 which is tilted to a straight 9, let's say. So if you would walk from this part to this part, we could go from something which is tilted to something which is straight. So what is really important to get out of the variation autoencoder is that now we can sample it really nicely, because the only thing we need to do is to sample from a normal distribution, and then we can just push, let's say, the sample through the decoder and get an image out. So this is what I'm doing here. Basically, I sample the latent space, say how many, let's say, images I want. So these are 10 images, and then I just run it through the decoder, which is really important. So only the decoder is needed at this part. Yeah. Okay, so let me see. There are no questions. Okay, variational autoencoder basically makes it much easier to sample. And here is the latent space after training the variational autoencoder. Okay, let me go back to the presentation. Now is the question, can we actually sample specific numbers? So when I showed sampling now, I just sample randomly and I get random numbers out. And it would be really nice if I could just say, okay, give me a sample from zeros, or give me 10 samples of zeros. And this, of course, is possible, but there is this limitation that you need to have the labels. So if you have the labels, we have it in the MNIST, so I'm going to show it. So if you have the labels, we can use them as additional input to the decoder. So basically, we will send the network the, let's say, the location in the latent space, and then we will also send in which category does it belong to. So this is basically how it looks like. So we do the same thing as the variation autoencoder. We have a mean and a variance. And then what we do is we sample from this distribution. And what we do in addition is we add also the category information. So we concatenate these two guys and make, like, say, a bigger latent space. And then the decoder, when he sees this category, he knows immediately which number he needs to, let's say, recreate. And then with, let's say, the location in the latent space, he knows how it should look like. And yeah, basically we're making it much easier for the decoder, because we already tell him which number he has to reconstruct. And of course, for this, we need to have the labels. So for each input, we also need to have the category or the label. So let me show this also in code. So same, input is the same, data preparation is the same. The model is the same as the variational autoencoder. There is nothing special here. We still have this, let's say, mean and variance. The only difference is in the decoder. He's not expecting any more 2 numbers, but he's expecting 12 numbers, because we have the latent size plus the number of categories. And because we have 10 categories, it's going to be 12. And because this number of categories is basically one hot encoded. So let's say for category 0, you go 1000 and so on. I think, yeah, this is for the people who do not know what one hot is. Okay, so 12 numbers as input. This is the only difference. And then the decoder is the same. So what we do basically in this forward pass is we pass in the input, create the latent space, like these 2 numbers from the latent space. And then we also pass in the category, and then we concatenate these 2 and then send this to the decoder. So now the decoder gets both the location in the latent space and the category. And then he can use this to decode or to create the input, recreate the input. Okay, again, load the model here. Again, we also load the weights immediately. Of course, I'm not going to do the training. Now, when we show the latent space, what you can see here is it looks really bad, the latent space. Everything is jumbled. So I will now ask a question, and I hope somebody on Twitch answers. Why do you think do we have a latent space now with all of these numbers jumbled around? And how can the decoder actually decode if everything is jumbled around like this? Okay, so there is a 30-second latency. I'm going to wait for, let's say, 1 minute maybe. Okay, so their messages are coming. Maybe not. Okay, nobody's answering. I don't know, maybe it's the latency. So I'm just going to continue and say, yes, nice. So I don't know how to pronounce this. Agrin. So Mr. Agrin, he has answered correctly because he said that you add the category, which is completely true. Because now we have the category that the network can separate. Because if we sample from here, we also tell them which category it is, so it samples nicely. And also, what is nice, if you could look at each of these individually, you will get the normal distribution. So basically what we have done is we have created for each category a normal distribution, which is awesome, because basically we need to sample only from a normal distribution and then also tell the category to get a sample out. So this is how it basically looks like if you do it. So you say here the category is 2. Basically, I went here for all categories. I go from 0 to 10 and show all of them like random samples. So here is like the category 0, and then you push in some sample, and then you get all kinds of zeros. Thin, small, and all of them are thick, but different shapes. And here also for ones, 1 but tilted differently. 2 is actually quite nice. They have like people are really artistic with the 2. So you have like really plain 2s with some kind of, and then you have some kind of 2s with, I don't know, weird shapes. 3s, and this is it. So basically what we have created now is, let's say, a variational it would be like we created several variational autoencoders. So you could also do it like this, like separate the data and then create different variational autoencoders for each number, let's say. But it is much easier. So you just give in the category and also then sample from the category. I need to scroll slower. So 5, of course, sometimes we also get the hole in the latent space. So then we get something like this. But basically now we can sample from each category. Okay, can you still guess the category if you are not sure what the data point belongs? Can you? No, you cannot, because the encoder, we made the life for the encoder much easier, because he does not need to know any more about the categories. He just has to put them somewhere in the latent space. And now he has the whole freedom of the whole normal distribution to place the numbers wherever he wants. So he's just pushing it somewhere. So basically I'm going to scroll back slowly. So the encoder is only putting it somewhere in here. And it is up to the decoder together with the category to guess which number it is. So basically here, I'm going to show it later in the unsupervised and semi-supervised one, where the decoder can also guess the category. Okay, one disclaimer. There are several ways how you can do this categorical variational autoencoder. There is a way where you teach the encoder to guess the category. But I like this. I didn't do it in this case. I like it much more because we get a nice normal distribution out, and then we just pass in the category to the decoder. So there are several ways how you can do it. In this example, the encoder is not guessing what category it is. The encoder is only generating the point, like 2 numbers, basically the point in the latent space. But of course, you could add here another term. Please guess the category also. Makes life harder for the encoder, but it's also doable. And I will show it later in the unsupervised one that I do exactly the same thing. So thank you for the question. Okay, so we sampled here from these different categories, and which is also nice. I have a nice representation now. If you say, give me a 0, but sample the whole, let's say, the whole normal distribution. So what you can see here, that how we move in the latent space actually changes features of, let's say, this number 0. So you go from, I don't know, almost a circle to something which is tilted and elongated. And then, I don't know, you go something which is big and round and thick and so on. So you really see how the network learns how to separate these different features. And I don't know if you saw, but there's a nice example where you go like with the GAN that creates the faces. And then when you go from young to old or from old to young, this is it. This is basically what they're doing. So they find your location in the latent space, and then they just push you in this direction. So let's say if you want to go from this kind of a 0 to let's say a bigger 0, you would just have to push like with a vector which goes in this direction. So basically you just determine where is this direction where I have to go, and then just push the sample here. So if you start with something like this, you push it in this direction, you will get something which is bigger. Let's say. And here I think I can find a nice example with 1. Yeah, okay, so this is actually, okay, I'll go from here. So this one is a little bit, let's say, tilted, and then if you push it in this direction, you will get, let's say, a straight one. And this you can do with all of them. I mean, of course, it's not going to be perfectly straight, but if you go from here to here, it's going to be straighter than it was here. With 2s, as I said, it's a little bit more artistic. So here we go from, actually, I'm going to zoom out a little bit here just to show you. I want to have it in one whole picture. So here, a little bit more, then I'm going to zoom in. Here we have a nice artistic 2 with this kind of thingy here. And then when we go to the end, we get a nice straight 2. So it's you can go like in the latent space in this direction and get a plane 2, let's say. And this happens for all of them. Okay, zooming back in, and I'm not going to go through all of the numbers, but basically all the numbers show some kind of features where you move from either tilting or being thick and so on. So let's see if I find something. Yeah, so this one is nice, basically going from a thick 6 to a really, let's say here, thin 6, which is straight. Okay, let me see if I have any more questions. No. Okay, now we have another question. Always having questions. Very cool, but I do not have any labels. What to do in this case? Well, after you stop crying, you could see if you have a student which can label it, who can label it. If you have a student that can label your data, you then use this categorical Y. It's the easiest thing. If you do not have, there is a way with unsupervised learning, but the thing is that you're not going to get good results as with the categorical evaluation autoencoder. And I'm going to show it right now in code. What I want to show before that is, this is a beautiful picture again. Now we have to talk about this Gumbel softmax a little bit more. If you remember, in the categories, I input, let's say, yeah, the categories basically are integers. They are not differentiable. Yeah, you cannot cannot do the differentiation through them. So you have now a different problem. It's not the problem that it's a normal distribution, or it's a like stochastic node. You have a problem now that it's, let's say, a categorical node, and you cannot pass information through it. So what these brilliant guys did in this paper, I put it here below, called categorical reparameterization with Gumbel softmax, is they created a reparameterization trick, but this time they do not use, let's say, so they use categories inside. So they created a reparameterization trick, but you can use categories. So what this means is that you can have your network output the latent space, output also the category, and then let's say recreate the image. And now you can also like back propagate through this category. And usually this is, I mean, it can be done. These examples here show ways where it can be done. Like you can have some kind of other branch which, let's say, somehow mimics this behavior, or you can say the gradients is 1, but this approach is way better. You have now a reparameterization trick where you use this really the category directly. So how they do it, this is Gumbel softmax. So this is the only, let's say, equations I have in my slide. So usually how you do this is you use an argmax function. So you just want to see like which from these is the biggest one, and then let's say you take this. However, of course, many of you know that argmax is not, you cannot differentiate through argmax, so you have a problem. So what they do is they basically skip or change argmax with a softmax function, which is differentiable, and they use a temperature, let's say, coefficient. And by changing this temperature, they can go from, let's say, a uniform distribution to a categorical distribution, and then sample from this categorical distribution. So basically what this means is that we can have a normal, let's say, linear layer, like a logits, And then we can use this Gumbel softmax to create our categories, which we need for, let's say, for the autoencoder. So this is how it looks like now. So now the encoder, this is like the question which we had before, does the encoder now know which category it is? In this case, yes, because the encoder has to guess the mean, the variance, and also the category. Then we sample from this distribution, which is called now the Gumbel softmax distribution, and then we do the same thing as in the categorical variation autoencoder. So you see that the titles are getting quite big: unsupervised categorical variational autoencoder. But yeah, really important. The only difference is now that the category is not given, but it is computed by the encoder and then sampled using the Gumbel softmax. Okay. So I'm now going to show you the examples and the code. So again, same. Here, which is something which is important, is previously I didn't use normals. I didn't, let's say, change the initialization of the weights. Here I did it because it's much easier to train. And if I did it also in the previous examples, it would be also easier to train. But I wanted to keep the networks quite simple at the beginning. So here I do some weight initialization to make it easier, basically, to train using a normal distribution with a really small standard deviation. And I use this for all of the layers except for the last one, and basically the one giving the categories, because I want the categories to be diverse. And I'm basically doing the same thing now with the decoder also. So what is different with the categorical variation autoencoder is that now we are also guessing the category. So basically, we get as an input some layer, and then we also guess with another, let's say, linear, with another linear layer, we guess the category. So now we also have to put in this parameter tau, which I mentioned. So this is basically going to give us how strict we are, or do we really want to have the categories, or we create, let's say, usually start from higher tau, higher coefficient, and then go to lower values, because you want the distribution at the beginning to be uniform, and then as you train, you force the network to decide, okay, which category is this number coming from, which category is this number coming from, and so on. And at the beginning, you leave it a little bit fuzzy so that the network can start to learn how to deconstruct stuff. Okay, so here is basically the encoder part, creating the same as with the variation autoencoder, creating the mean and the variance, using this to sample. Here basically sample from the latent space, and then here now creating the logits for the category, and then using this Gumbel softmax. This is basically for me for debugging. So this is, well, just a softmax if you want to visualize it. This is the log also used for debugging, but this is basically the only difference now, that we also use this Gumbel softmax to also sample from this distribution, and we also have to pass in the tau, this parameter. And yeah, so basically we sample from the normal distribution, create the sample in the latent space, and then we also sample the category. So after training, of course, I'm not going to show it right now. So after training the model, we have a latent space which is the same or similar, not, of course, not the same to the categorical variation autoencoder. Basically, everything is jumbled, but we have this additional information of the category. Basically, we get the same as before. We get, for each number, we get, let's say, a normal distribution. We should get, of course, it's not perfect, but we should get a normal distribution. However, now come the shortcomings. You cannot force the network to learn what you would like to learn. So maybe you would like to have at each class a different number, but the network does not know anything about numbers. So it's just going to, you can say how many categories you want. So I, of course, put this to 10. But how and which numbers the network puts into categories, we cannot influence this. So basically what we get, I'm going to show you. So the first category, it seems like the network chose the number 3 to put in the first category. And you need to know also that this is random. So if you retrain this network, you could get different results. Second category, it seems like it's 6. Okay, so far so good. Third category, zeros. Okay, good. 7. Okay, in the fourth category. 2 in the fifth category. This is also good. But now, okay, so what happened right now? So our network somehow decided to put different 2s in different categories. And yeah, unfortunately, there is no way for us to influence this. So for some reason, this 2 created one category, this 2 created another category, and this is how the network learned. I mean, this is still better than nothing. You can get some, let's say, useful categories, but this is something which can happen, and you cannot influence it in any way. It seems like this group 7 is really bad. Nothing specially was learned here. Maybe some 4s and 9s and 7s. 8 is a mix of 5 and 8. Yeah. And okay, 9 is again zeros, so maybe different kinds of zeros. And 10 is it's kind of mixed with 1s and something else. Okay, so now we see the limitation of the unsupervised learning. So the unsupervised learning, you will get your categories. You can sample from the categories, but you cannot influence the categories, and you do not know if they're going to be good or not. Here again, I show the slices from the whole, let's say, normal distribution. If I could go back. Yeah, and I show samples, let's say, for the first category. It seems to be mostly 3s, but it's also 5s and 8s and so on. So everything mixed together. And if you look at different categories, you can get, sometimes you get a good class, like good category. So let's see here, it's all 6s. So this is really nice. This could be useful. But again, you cannot influence this. Maybe next time it's going to be 5s and 6 are going to be mixed with something else and so on. So I want to, okay, show you another one. So this is also a nice class with all zeros. Let's see, I want to find a failure case. Okay, this one, it seems it did not learn really good this category. So here we have some garbage. And here at the end, we have some 2s. So basically, it seems that 2s were a problem in this run. Of course, if you rerun it, maybe something else could happen. Okay, so now that we have shown that unsupervised can be used, it's not perfect. It will learn some categories, but you cannot influence it. Now comes the question, of course. Okay, give me a second. If you, there is a question. If you, okay, nice. Somebody just asked a question, which I'm going to, of course, answer now in my next slides. So when I said that there is no way to influence the network, it's true, but it's also not true. We can influence it if we have some labels. So this is where the semi-supervised part comes in. So if we teach the network what it needs to do, at least with a little bit of data, then we can hope that it's going to transfer, like let's say, this knowledge to all of the other, let's say, extrapolate to all of the other data. So usually you take like a small subset, 5–10% of your data, label it, and then use this as your starting, let's say, position for the unsupervised clustering. And this helps a lot. So this is basically my next slide is basically a question again. Yeah, this just visually shows our problem. And maybe I'll spend a minute on this. So we have some data. Let's say we have here circles, and then we have like these squares, and they have different colors and so on. We cannot influence currently how the net, like if you do not do anything, like if you do not label or do anything, we cannot influence how this is separated. Maybe the network separates it like this. Maybe it separates it by, this is by shape, this is by color, and here it's by, let's say, shape and color, but let's say the circles are, I don't know, here is like by color, and here is by shape and color. The shape is closer, and the color is then, let's say, further away. So if it's unsupervised, you can get any of these cases, you cannot influence. The only thing we can influence is the number of categories, let's see. Okay, so semi-supervised categorical relation autoencoder, the same thing. It's basically the unsupervised network. Everything is the same. The only thing what we're going to do is use pre-training. So we're going to take some label data, 5% in my tests, and then see if we get better classes out. Yeah, okay. So I just checked if there's another question. So basically that's it. Let's do some pre-training on the unsupervised and then train on the whole data set. So this is it. Let's jump to this notebook. Now there is literally no change between the two networks. Basically, I use this also the same name. The only difference is that we have pre-training. Sorry, can you repeat, Herbert? Yes, okay, I need to zoom in a little. Herbert is backstage helping me. Okay, so basically no difference. Unfortunately, I copied this code. I need to add here the other the pre-training step. I forgot to add it in the code, but basically when I trained it, I had it. So when you get the code, you will also have, let's say, pre-training the model. And when we, of course, do some pre-training, there are several ways how you can do this pre-training. And I'm not going to go too deep into this. Like you can train on one, then train on another, or train at the same time use some samples without labels, some with labels. So there are ways how you can train this. I use the easiest one where I just pre-trained first, trained and iterated a couple of times, then let's say pre-trained again, then trained again and so on. And yeah, basically a couple of rounds and I saved the model. But as I said, there are ways, and there are better ways how you can do this. Okay, so if you show the latent space, similar to the categorical, I do not know. In this example, it seems that he separated something, but he didn't have to do it. But yeah, maybe the network used it a little bit. But what is interesting right now, yeah, I forgot. I said it before, but I'm going to mention it one more time now. I just used 5% of the data, and I randomly selected these 5%. And there are better, of course, ways how you can select these 5%. Maybe you can use unique ones, crazy ones, and so on. If you do manually, you can search for what you think could be hard for the network and so on. In this example, I just used randomly. Take just 5% randomly out of the data, which is also maybe not good because you could miss some classes. So you need to shuffle your data really good for this, because in the MNIST data set, you have the numbers in order. So you have to shuffle them really good and then just take 5% out. Okay. Yes. Okay, let me read. Okay, let me read to this question. You mentioned that autoencoders tend to produce fuzzy lines, unlike GANs. Is this specific to variational autoencoders? Because you're training off the distribution in the latent space and simply optimizing the coded format. So it is true in general for autoencoders, and I do not have some kind of mathematical proof for this. It's just that I experienced this by experimentation. The thing is that the GAN is looking at the outputs and compares the outputs, and for the GANs, it's really easy to notice when it's fuzzy and when it's not fuzzy, and then you will. So the let's say the discriminator would learn this really quickly. So he would really quickly pick out when the output is fuzzy and when it's not fuzzy. So the GAN has to make lines which are not fuzzy. And with the autoencoder, because we're using, let's say, a loss function, which is, let's say, mean squared error or yeah, something like this, it doesn't get penalized for this fuzziness, let's say. Yeah. So the GAN gets penalized for the fuzziness because the discriminator will find out that he is doing the fuzzy thing. And in the variational autoencoder, this is not the case. So basically, yeah, you get the fuzzy lines out. Okay. Maybe somebody in the discussion can give more insight. Yeah. Okay, so now I'm just going to show you the samples after doing pre-training. So first of all, what you're going to notice is that now the classes are ordered in a nice order because we created this order. We said that we want to have zeros in the first category, ones in the second category, and so on. And what is nice is that we can also now sample from it. So basically, we get the categorical variational autoencoder, but only with 5% of label data. This, let's say, the quality is not so good, but it could be also that I could have trained a little bit longer. So the quality in general should be good. Yeah, here maybe just sampled from a wrong location. The tools are also nice. You can see that you get different tools. It's really important that in your pre-training you have also different kinds of tools. I didn't do it, but if I would do this seriously, I would really try to get different kinds of, let's say, tools into my pre-training data set, because I want to learn my network, teach my network to put these actually into the same class. Again, nice 3s, nice 4s, 5s here, maybe somewhere sampled really far away. 6 is also nice. 7, 8, and 9. Okay, and I have at the end just a nice representation now with the whole latent space, so we can have a look a little bit. The zeros, it seems like on the left corner he had some trouble, but the rest of it seems fine. Yeah, the zeros are nice. And okay, yeah, this is also once we had problems. So as I said, I do not know. Maybe I could have done more training. So I cannot comment on this either, that maybe with more training this could have been learned better. But at least we only have ones. There is no other numbers moved in. Maybe a 3 here. Tools are really nice, different kinds of tools. And so on, yeah. So basically this is it what I wanted to show in code. Let me just then scroll past all of this. Yeah, maybe I should show the 8s. 8s are really nice. People tend to write 8s in different ways, so like thin, or let's say not wide, tilted, big, thick, and so on. So you can really go through the latent space here. See like these crazy small 8s and so on. Okay, now back to my presentation. So I wanted to show you or highlight this paper. So basically, most of this research which I showed this evening was done 3 or 4 years ago, and maybe 3 years ago. And I really thought that GANs are going to they took over completely, and that there is the variational autoencoders are, we should not use them anymore because GANs are better. Even though GANs are harder to train, but they give better performance. And then in 2020, so basically this year, I read this nice paper called Bringing Old Photos Back to Life. And they do a really amazing job in basically reconstructing old images. And it's not only getting like past these creases and correcting those, but they also correct the color and get rid of this noise and so on. So you see, I mean, this picture is awesome. The interesting part in this paper is that they didn't use generative, so the GANs. What they use is basically 2 variational autoencoders, or basically 3. 2, but they use different data. So I'm going to explain it right now. So they used variational autoencoders, and the idea is really, really great. This is one of these papers where you read it and then you go, oh my God, this is so simple, so easy to understand, and so awesome. They have 2 sets of images. One is synthetic and one is real. So they created, let's say, corrupted synthetic images. So you take any kind of image and just add your corruption, like add these, let's say, noise, simulate these kind of, I don't know, creases and so on. And then you teach a variational autoencoder to go like from the corrupted input to the like recreate this corrupted input. But what is really, really interesting is that you use corrupted real images and do the same thing, and force these 2 distributions to be the same. So basically, you force the distribution of your synthetic data and the distribution of the real data to be the same. What this means basically is that you can sample from this, let's say, distribution, which should be the same. And then it doesn't matter if you sampled like synthetic corrupted data or real corrupted data. Why is this useful? Okay, now we have 2 distributions and they're the same. Why is this useful? Because okay, just let's say this is some kind of mapping. It doesn't matter. So this is kind of a mapping where you go now to a different latent space. So we are now, you just go from this now latent space to another latent space. And what we can do from this other latent space is we can try to reconstruct let's say, clean images. And because we have our synthetic data, we have our clean images. So what we do is we go from our corrupted synthetic image to this latent space, we do a transformation to this latent space, and then we teach this guy to create, let's say, the nice image out. And basically here is also like this guy is only working with nice images. So he learns how to let's say compress and decompress nice images. And then we have a mapping between our corrupted latent space to our, let's say, nice latent space. And then if we train this well, we can train our network to take our synthetic corrupted image, get the latent space, move it to the other latent space, and reconstruct the nice image. And what happens in the end when you do the training is that you can take a corrupted image, get the latent space here in this, let's say, corrupted space, move it to this, let's say, good space, and then get the image, like the clean image out. So basically, we have with our synthetic data taught our network how to jump between latent spaces and create, let's say, a nice image. And because we forced our distributions to be the same, we can now just put in corrupted data and get nice data out. And this is basically what they show here. My point in showing this paper is just to share with you that I think variational autoencoders have lots of uses in the future, and you never know what somebody will do with them. Yeah. So basically, this concludes my talk. This presentation is going to be online. So you will yeah, you will get this, and you can also then check out these two papers. One is with the categorical representation with Gumbel softmax, and the other one is bringing all photos back to life. Okay, I will just answer these questions really quickly because I think they could be also interesting for people listening. Okay, Okay, so if you okay, this I already read. Okay, does this file use self-attention? No, I didn't use any self-attention. So this, I wanted to, so there are, if you look at these autoencoders and variation autoencoders, there are so many of them. Like there is a whole, I don't know, zoo of models you can find on GitHub and so on. What I wanted here to give you a little bit more intuition on what they do and what you can use them for. This is basically vanilla convolutional autoencoder and variation autoencoder. There is so much more you can do with this. Okay, you mentioned that there's okay. How similar do the distribution have to be? But really amazing. Yeah, this is a nice question. So I don't know. There is no definite answer. It basically probably running and checking. This is also with variation autoencoder. You do not know when to stop training, basically, because the error at some point stops to decrease, because you always have these small differences. Sometimes you even miss the label, so your error accumulates. So there is no definite answer when are the distributions close enough and when is enough training and so on. Yeah. Okay, so this is it. These are all the questions. Thank you very much for your attention. Sorry for the, let's say, the technical problems we had. And I really hope that you learned something. And please join us in Discord. I'm going to be there, and then we can, yeah, just discuss. And if you have any more additional questions, we can discuss them there. So thank you very much.
So thank you very much to our audience. I pasted the Discord link. You will also be able to watch Lil is echoing. So I also pasted the, there will be a, you can watch this on YouTube, and if you're in the meetup group, you're getting all the links. Thanks for your attention, and see you in the Discord.
Small things are the most meaningful. So this holiday season, I simply enjoy fresh sparkling water with a nearly extinct friend.
Der Schnupfen-Hack-Check, powered by